Welcome back, guys. Welcome back. Good morning, guys. Good morning. Good morning. Yeah. So welcome, guys. Welcome to NEET World Institute. So in this session we are going to particularly see about the top topics in the physics which we are going to cover in the 100 days challenge. Okay. So in previous session we have seen about the NEET PYQs na. So this session is particularly for top topics, 100 topics in 100 days. Yes, we have stopped up to, yes, this is the topic which we are going to see in this particular session, that is Bernoulli's theorem application. Okay, let us go into the topic. First we will see what is fluid dynamics. Like, to study fluid motion, instead of tracking individual fluid particle using Newton's law, we observe how properties like velocity, pressure behave at a fixed point in a space. Okay, this is about the fluid dynamics, like the study of fluid motion we will say. Next, assumption to simplify fluid flow analysis. So first one non-viscous, second one is steady flow, third one is rotational flow. So first one, no internal friction between the layers, like when one layer and another layer, like water is there and a pipe is there, there will be no internal friction between the layers, no energy loss. Okay, and steady flow, fluid properties at a point do not change with respect to time. Okay, so velocity and pressure will not change. And irrotational flow, a tiny pedal wheel in the fluid does not rotate, no angular momentum. Okay, no angular momentum. When there is no rotation, there will be no angular momentum, right? Next is type of fluids. So there are 4 types, like steady flow, second one is laminar versus turbulent, third one is compressible versus incompressible, and fourth one is rotational versus irrotational flow. So first one is steady flow. Velocity at a point does not change with time. That what we have seen in the last slide. Next, particles follow streamline, like a path that never crosses. Okay, particles follow streamline. Okay, the next thing is laminar and turbulent. Laminar is nothing but a smooth orderly layer, and streamline are parallel. Okay, and turbulent irregular, like it will go in irregular shape, and like energy will be losses, like when one layer and another layer clashes, the energy has been lost there, we will say. Okay, and compressible versus incompressible, so density changes and density will not change here in incompressible. So compressible density will be changed and incompressible density will be constant. So compressible common in gases, like density constant in the sense like usually in the liquid we will say. Okay, next is rotational versus irrotational. So rotational particles spin around their axis, irrotational particle do not spin, just move forward and backward directions, that's it. Okay, this is about the types of fluids to fluid flow. Okay, next one is the principle of continuity. Principle of continuity. The velocity of a fluid particle can vary along a streamline, as a fluid flow through a pipe of varying cross sectional area. The product of area and velocity must remains constant. Okay, that's what the principle of continuity says, like mass flow rate of section 1 should be equals to mass flow rate of section 2. So rho A V, like delta L1 they have given, so and this one is rho A L. So where density is common, density is common, so I can say that A1 equals to A2, A1 V1 equals to A2 V2. Okay, like a fluid is incompressible, that what we have studied, like for gas it is compressible, for fluid it is incompressible. We have for gas, yes, for gas it is compress, for fluid incompress, density is not constant, density constant. Okay. So speed increases where area decreases, and streamline are denser where velocity is higher. So denser velocity is higher. Velocity high means density will be high. Density will be high. And then what about speed and area? Speed increases, area decreases. That is, velocity increases, area decreases. That's what now. Because when I take a1 a v equals to constant, a v equals to constant, yeah, a v is equals to constant, so a is inversely proportional to v. So whether velocity increases, area will decreases, area increases, velocity decreases. Okay. If you want, you can take a screenshot of this. We'll go for the next slide. So next is Bernoulli's equation. Like Bernoulli's equation we know, like P plus rho g h plus of rho v square is always equals to constant. So applies to non-viscous incompressible steady flow. So Bernoulli's equation is derived from the conservation of mechanical energy of fluid properties. Okay, like pressure, potential energy and kinetic energy should be equals to constant, right? That's what we have studied now in Bernoulli's. So whatever we are studying here, just a recap of that. So pressure plus potential energy plus kinetic energy should be constant, right? So P plus rho g h plus of rho v square is equals to constant. Okay, this is about the Bernoulli's equation. So remember the formula, P1 or P plus rho g h plus of rho v square. Okay, this one formula we have studied. One more formula is A1 V1 is equals to A2 V2. Second formula. Okay, two formulas we have studied now. We go for the next one. Yes. So application of Bernoulli's theorem. So speed of efflux. So speed of efflux in the sense, like when I consider a box or anything, okay, or a drum is there. So when I make a hole on the drum, okay, so a velocity of a particle from a velocity of a fluid which is falling from the top of the drum to the ground level. So velocity, if I need to find, it is under root of 2gh. So initial velocity will be 0. At final, what will be the velocity they are asking? So under root of 2gh will be the answer. So next is Magnus effect. So spinning a ball causes different velocity of air on its two sides, so creating pressure difference. So this effect, no, you would have watched in like when they are playing football. Okay, so Magnus effect. Like if you remember the Roberto Carlos, when he kicked the ball towards the net, so you use the Magnus effect, right? So next is aerofoil. So an aerofoil is shaped such that an air moves faster over its curved top surface. So pressure above decreases, pressure below remains high. Next is result in net upward lift and used in airplane wings. Okay, this is about the application of Bernoulli's theorem. So first one is speed of efflux, Magnus effect, aerofoil. So next we will go into the questionnaires. So water is pumped from a depth of 10 meter and delivered through a pipe of cross sectional area. If it is needed to deliver a volume of 10 power minus 3 per second, the power required. So power formula, what is the power formula? First of all, the formula for the power, it is power equals to work done by time or energy by time, we will say. Power is equals to work done by time, or else we will say energy by time. Okay, so both are correct only, work done by time or energy by time. So in this I need to find the energy, right? So per second they are asking, per second no, so per second in the sense t is equals to 1. What about the energy? So energy, like it's falling from, delivering from the top, no, up. So rho g h into q, how much energy is, like q is given, right, depth is given, h, that is undelivered volume 10 power minus 3, and the cross sectional area is given. So density of water is, it's water, no, it's water, right, density of water rho is equals to 10 power 3, height 10 meter, h is equals to 10, g is equals to 10, this meter per second square. And what about the q? Q is nothing but deliver a volume, okay, 10 power minus 3, right, flow rate, no, flow rate, cross sectional area, volume, density, yeah, you can find it easily. So if you substitute these values in that equation, E is equals to rho g h q, volume flow rate is nothing but 10 power minus 1, 10 power 3 minus 3 divided by 10 power minus 2, yes. So this volume and this area, flow rate they are asking, 10 power minus 1. We will go for the next question. Yes. A tank has an orifice near its bottom. The volume of a liquid flowing per second out of the orifice does not depends on. So area of the orifice, height of the liquid level above the orifice, density of a liquid, acceleration due to gravity. So it does not depends on, obviously density, right, obviously density. So it does not depends upon the density of the liquid, like area will be there, height also will be there, acceleration due to gravity obviously will be there, it does not depend upon the density of the liquid. So next question, okay. A tank is filled with the water up to height of 1 meter, okay. A hole is made at a distance of 20 centimeter from the top. Find the horizontal distance from the base of a tank where the water strikes the ground, okay. So I need to find the range, right, range in the sense the distance I need to find here. So speed equals to distance by time, where range is nothing but velocity into time. So I need to find the velocity, I need to find the time also. So what will be the velocity? So root over 2gh, root over 2gh, and time formula it is 2h by g, yes, time formula t is equals to root over 2h by g. So from this two equation I can find the velocity. First one, it is nothing but 2 into 10 into, what is the value of height? From this, no, height is 0.8 meters, 80 centimeter, right, 0.8 meters. So 0.8, which is nothing but root 16 is equals to 4 meter per second, 4 meter per second. What about the time? From this I need to calculate, it is under root of everything is given in centimeter, we can convert, yeah. So it is 2 into 0.2 divided by 10, which is equals to 4 divided by 100, under root of 4 divided by 100, 2 by 10, which is 0.2. Okay. Now range equals to 4 into 0.2, which is nothing but 0.8 meter, 0.8 meter. So 80 centimeter is the answer, 80 centimeter is the answer. So whatever formula we have seen, those formulas only we are using here. Okay. So like these are the formulas which we have seen in the kinematic itself. No, velocity, time, everything. Okay. So this is velocity of Flex. Once again we have seen here. So next question. Yeah. A water is flowing in a pipe of a diameter 4 centimeter with a velocity 3 centimeter per second. The water then enters into a pipe of 2 centimeter diameter, that is diameter of 2 centimeter, velocity of a water in other pipe. So one pipe velocity is 3 meter per second, diameter is 4 centimeter, another pipe diameter is 2 centimeter, and what is the velocity they are asking. So I can use the principle of continuity, here, principle of continuity, that is A1 V1 is equals to A2 V2, where area of the pipe, so it is pi r square. So can I say that R1 square V1 is equals to R2 square V2, because pi is the constant term, so I can cancel it out. So what about the diameter? Diameter here it is 4 centimeter, so radius will be 2 centimeter, so which will be in meter, nothing but 2 into 10 power minus 2 the whole square. V1 is 3, divide by, what about the V2 I need to find, what about the like radius of the second one, 1 into 10 power minus 2 the whole square should be equals to V2, that's it, no, easily I can find. So obviously it is 4 into 10 power minus 4 into 3 divided by 10 power minus 4. So 10 power minus 4, 10 power minus 4 will get cancelled, and V2 will be equals to 12. Yeah, 12 meter per second is the answer. 12 meter per second is the answer. Yes. So we will stop up to this. Okay. We will continue with the next class. Okay guys, bye. We will see you in the next class. We will meet up in the next class. Bye bye.